flight controls, electrical, and airframe systems. Aircraft components. We're going to look at the parts of an airplane first and go from there. So the first thing we're going to think about is the fuselage. The fuselage contains two major components. The cockpit, that's where the pilots sit, and if you've got an older airplane, a flight engineer would sit there also. And then you have the cabin, that's where the passengers sit. In small airplanes, the cockpit and the cabin is all lumped in together in one place. You can't really separate out the cockpit or the cabin. Here is a fuselage. You notice it doesn't have the wings, the landing gear, the vertical stabilizer, the horizontal stabilizer. It doesn't have the empennage. It's just the fuselage. And of course, you can see here the cabin. Let's see. If I was going to draw the cabin cutoff here, the cockpit would be here forward, and the cabin would be there aft. So if we look at, oh, that was pretty interesting. So if we look at construction, an open truss framework, people aren't using that very often anymore. That's pretty old school. Here's a picture of open truss. You can make it out of wood. You can make it out of hollow steel tubing, but it weighs a lot to get the amount of strength that you need. A monocoque type of construction has stress skin, where the stress skin is the only thing that's holding the stress or the load or needs all the strength, with maybe a little bit of structure. Here's a picture of a monocoque skinned fuselage, and you'll notice right in here and in here there's no longerons, there's nothing that's going back to take the load except for the skin. Semi-monocoque is a type of construction that is found in the vast majority of small, medium, and large airplanes, and that's where the skin takes some of the stress, some of the load, and that's where framework built into it or attached to it also takes some of the load. So here is an interior cutaway diagram of a pretty typical fuselage aft of the cabin or aft of the cockpit on a small airplane, where the skin carries some of the load, and so does the internal structure. That's semi-monocoque, and that's what's found in the vast majority of small, medium, and large airplanes. Wings. Okay, high wing, low wing, mid wing, and biplane. So there's a lot of different kinds of wings, but they're all doing the same thing. They all contain the same components. As for instance, the major component is the airfoil. The purpose of an airfoil is to generate lift. The ailerons are there out on the wingtips usually, and they're to create differential lift so that you can roll the aircraft. For instance, if we had a wing and a fuselage with a propeller on it, and we'll put an empennage on it, the ailerons are typically on the outboard on the left and right wing, and one aileron moves up and the aileron moves down. So if we look at this one over here, if here is the wing and then here is the aileron that's gone up, the airflow across the wing is going to hit it, and it's going to push this wing down. So that means this airplane is going to tend to roll to the left. And of course, at the exact same time, this aileron on this wing is going to go down, so the airflow is going to hit it, and it's going to push this wing up. So this wing goes up, which also contributes to a roll to the left. Now, what's interesting is that, well, we'll get into some more aerodynamics later. So ailerons provide differential lift. Flaps create lift and drag. So if we have a wing and we put in flaps, then air's going to hit it, get knocked down, and this wing's going to go up. So we get more lift. That means we can fly at a slower airspeed, but the wind is hitting the flap, and the flap is trying to slow down. That creates drag. So that means that we're going to have to either add power or we're going to have to nose the airplane down in order to maintain our airspeed. So flaps generate lift and drag, and of course this makes it really nice to come in and do an approach to land, because one, a lower speed, if we can fly at a lower speed, that's going to equal a shorter runway. And if we have more drag and we point the nose of the airplane down, that means that we're going to be able to have a higher descent rate. Which, if we're coming into land, sometimes we like to have higher descent rates. Empennage. The empennage is also called the tail surfaces. Or if on this aircraft, if you wanted to say empennage, you'd say the empennage starts here and is everything back. So on this aircraft, we can see the vertical stabilizer, we can see the rudder, we can see the horizontal stabilizer, and we can see an elevator. Of course, you can also see this airplane. It has flaps extended, and it's hard to see the ailerons are neutral, but that's where the ailerons are. So vertical stabilizers allow for, or cause, or the purpose of vertical stabilizers is to have stability in yaw. If I can hit the right buttons here. So if here's our airplane, where'd that line come from? And here's our vertical stabilizer. So we're looking down on top of the airplane. Here's a horizontal stabilizer. But let's look at the vertical stabilizer. If this tail tries to go off to the side, then the slipstream coming down is going to hit the tail and push it back. So if here's our fuselage and here's our vertical stabilizer, and if because the airplane yawed to the right, the slipstream or the airflow is going to push that tail and make us go straight again. So that's how the vertical stabilizer gives us stability in yaw. The rudder gives us yaw control. We want to be able to yaw the airplane left or right. So here's our airplane, here's our vertical stabilizer, but then here's our rudder, and we can of course turn the rudder left and right, and we can control the yaw of the airplane. The horizontal stabilizer provides stability in pitch. So if we look at the side of an airplane, let's draw a tomahawk here, pretty lousy tomahawk, and here's our horizontal stabilizer. Again, if, well, let me try it this way. Let's draw it. Let's say the airplane is pitching up, and here's our horizontal stabilizer. If the airflow comes and hits it, it's going to tend to push the tail up and push the nose down, and therefore it gives us stability in pitch. Now, if we then add, the next item is going to be the elevator. If we put the elevator on the back here, we can control the pitch by making the elevator go up and down. If the elevator goes up, then the air hits it, and it pushes the tail down, and it pushes the nose up. So we're going to use the elevator for pitch control. Trim tab. The trim tab is there to maintain elevator position. So just say here is our horizontal stabilizer, and then here is our elevator, and then we could put a trim tab on the end of it. And if we move the trim tab up, the airflow is going to hit it and push this whole elevator down. Now the airflow is going to hit it, and it's going to push the tail, the whole tail up. So really what the trim tab there is to keep the elevator in the correct position so that you as the pilot don't have to push or pull on the trim tab. But if somebody said, hey, what's the trim tab there for? You would say the trim tab is to maintain elevator position where I want it. If, in lieu of an elevator and a trim tab and a horizontal stabilizer, you can instead have a stabilator. Oh, darn, the picture didn't work. So why that's all moving that fast. In any case, a stabulator is where you have the elevator, you have the horizontal stabilizer, and an elevator in the same device. And it's pretty common on a lot of Piper aircraft, except for it's not on a PA-28. So if we look at it from the side, here's our stabilizer, and then we have an anti-servo tab on the end, and it hinges right around here in the middle. So if we want to go up, stabilizer here goes up, down, here it goes up, and so now the stabilizer and the anti-servo tab or the trim would be right there. Now air hits it, pushes the tail down, and then of course the nose is going to go up. You'll notice how, though, I drew this trim tab or anti-servo tab, I drew it a little differently. As this entire stabulator, the entire tail surface moves. That is, the stabilizer and the elevator is one piece, so the whole thing moves. This anti-servo tab, when the stabilizer leaves neutral, this anti-servo tab actually moved up a little bit, and now the air is hitting it, and it actually makes it harder for the pilot to go to full control travel and pull the nose back. That way it prevents over-controlling, because the anti-servo tab moves in such a way that it gets in the way of the slipstream, the airflow, and makes it harder to move the control. The other thing it does, just like a trim tab, it's also there to maintain stabulator position. So if I crank in the aircraft and I rotate that trim wheel and I rotate it and I move this anti-servo tab up, then the airflow is going to hit it, and it's going to make the stabilizer go down. And of course, now here's our anti-servo tab. Now air is going to hit it and get knocked down, and that's going to make the tail go up and make the nose of the airplane go down. But it will hold, again, it will maintain the stabilizer, or it will hold the stabulator in position. So this anti-servo tab really does two things, only one of which is what a trim tab does. The second thing that an anti-servo tab does is prevent the pilot from over-controlling. And again, the stabulator is doing the same two things as the stabilizer and the elevator. It's there for stability in pitch, and of course it's there so pilots can control the pitch. Okay, next is landing gear. So conventional landing gear versus tricycle landing gear. Let's take a picture, take a look at this. This is a J3 Cub. It's a really early Piper from the 1930s. They made them for decades and decades and decades. And I want you to notice that there's two main wheels in the front and that there's one small tail wheel in the back. And this can be called a tail wheel airplane. Sometimes it's called a tail dragger. And that's in addition to the fact that it's also called conventional. Conventional gear. So what I want you to also notice is that the center of gravity of the airplane is behind the main wheels. So when this airplane is sitting on the ground, the center of gravity is toward the back, so that helps keep the nose down. So if you're landing a tail dragger off of the airport and there's a gopher hole that you run into, it's less likely that the nose will go forward and hit the propeller, which is why you see a lot of, I was going to say off-road, you see a lot of airplanes that fly off airport, such as Bush airplanes in Alaska or other countries, and they use a lot of tail draggers there for this main reason, so that you can land on unimproved runways, that is dirt strips or grass fields, and it's less likely for the nose to go forward and hit anything. So here is a nose wheel airplane, and of course here is the nose. We have two main gear, and it's hard to see right here, but the center of gravity of this airplane is actually now in front of the main wheels. So if this is where the main wheels are, right here, center of gravity is farther forward, and that keeps some weight on the nose wheel and so the airplane tends to go forward a little tiny bit. So this airplane, or this type of landing gear, is easier to take off and land. It's easier to take off and land. In a tail dragger airplane, you have to use the rudder a whole lot more than you would in a nose wheel airplane. And that's what gets nose wheel airplanes in trouble with flying tail draggers, is that they aren't used to using enough rudder. So if you're ever going to transition to tail draggers, make sure you use a whole bunch more rudder. Okay, we showed the main wheels, a nose or a tail wheel. Fixed gear versus, and also I said a nose gear airplane. It's an airplane that has tricycle gear. It has a nose wheel, and conventional gear have tail wheels. So let's take a look. Fixed gear means the landing gear doesn't go up or down. It stays bolted to the airplane, and it causes a lot of drag. Retractable gear airplanes, the landing gear pulls up after takeoff, and now the landing gear's not sticking out, so we have noticeably less drag. So the trade-off is you have less drag and you can go faster, but now the airplane costs more to buy, it costs more to maintain it, and it's more complicated. You have one more thing that could break. Okay, let's talk about shock absorption. When you land the airplane and it's not as smooth as you'd like, it would be really nice if when you hit the ground, those shocks don't get pushed all the way into the airframe. So we need something in our landing gear to absorb some of that shock. On a Piper Tomahawk and a lot of other small airplanes, this landing gear right here is made out of spring steel. And it's not just regular steel, it's spring steel, because that means it will bend and bend right back. In fact, you could argue it springs. It doesn't actually bend. So when you land really hard, this will come out, and then it'll go back to where it was. And that slows down that, or rather, it increases the length of time that the airplane is decelerating over a longer period of time. So it's not just like getting hit with a hard hammer. There's also a thing called oleo struts. Oleo struts are also called air oil shock struts. Air oil struts. And inside of this strut in here, and I'm going to oversimplify it a lot, there is compressed air. There's actually a valve on top like a bicycle or a car tire, and there's compressed air in here. So when the airplane lands hard, this air in here gets compressed, and that allows this strut to go up. But also fluid, or hydraulic fluid, is going through a little tiny hole. If I drew that a little better, it would look like this, a metered orifice. It's a really tiny hole. So when this strut gets pushed up, red 5606 hydraulic fluid gets pushed to this really tiny hole, but it can't all go there at once. So it slows things down, so it takes longer for this strut to get compressed or pushed all the way up in there. So an air oil shock strut really has two ways to absorb shock. It has compressed air and it has hydraulic fluid, or hydraulic oil if you prefer, to also help absorb the shock. Okay, brakes, airplane brakes. The vast majority of airplane brakes are disc brakes. They weigh less than drum brakes, and they're less complicated, and they work better than drum brakes under most conditions. There's two major components to disc brakes, the disc and the brake pad. I'm going to show you a picture here shortly. One nice thing about brakes is that it allows differential braking. That is, you push on one pedal and it applies brakes to one wheel, one main wheel. The other pedal applies brakes to the other wheel, and of course that helps with steering, especially when you're going slow. And of course you can have a parking brake. And in fact, I think I got a picture here shortly. Brakes, in addition to the air oil shock strut, brakes use 5606 hydraulic fluid, which has red dye in it, so that if there is a leak, you're a lot more likely to be able to see it, which is, oh yeah, there we go, leaks. Same thing for brakes. Brakes also use 5606 hydraulic fluid, and it has a red dye in it, so it's easier to find the leaks. Okay, there's my picture. So here's some brakes. So you push down on the toes. this master cylinder right here tries to squish the brake fluid, but it doesn't compress, and it goes out and it pushes the discs together. There's a disc on one side and a disc on the other, and when the hydraulic fluid gets down here, there's a piston and it pushes the discs together and grabs onto that disc and that friction. So your inertia of the airplane gets turned into friction, or actually via friction gets turned into heat, which is why the brakes get hot, which is one reason why you don't want to ride the brakes with your toes all the time. So obviously on the other pedal, you push down and brake fluid goes out and squishes those brake pads against the brake disc. When you pull on the parking brake handle and you set it, you're actually pushing a piston, and it pushes the brake fluid out to both of the wheels, and then pushing the button locks it so no more fluid can go backwards, and that way pressure stays inside of the brake system so that the brake pads are pushing on the brake disc all the time. That's the parking brake. And there's another picture of a disc. So here you can see the disc. And sometimes disc is spelled with a C instead of a K. And okay. All right, we're going to do the same thing with the fuel system that we did with the electrical system. The fuel system on a PA-28 and 38 are nearly identical. In fact, I looked at the schematics in both the POHs, and if you draw them, they have the same components. So we're going to say that they are the same. So we're going to call this the simple Piper fuel system that works for both airplanes. So I recommend you pull out this diagram and label as we go along. So let's see. Here's a tank, fuel tank. And here's our filler cap. And we have a vent. And just to make it less cluttered, we have the tank drain. And we have a fuel gauge. And we have a fuel selector valve. Fuel, see if I can make that all fit. Selector valve. And on the fuel selector valve, we have right, and we have left, and we have off. There's 3 positions. You'll notice that this fuel pickup tube right here, it's not at the bottom of the tank. So as long as the fuel level comes down to here, we're still going to be able to get fuel. So effectively what that means is inside of here, if I can get it to go, this is unusable fuel. It doesn't want to do it. Let's see if I can do it. No, it doesn't want to let me do it. So I'm going to write it. I'm going to write it up here. Unusable fuel. But I'm talking about this fuel down here in the bottom. I'm talking about this fuel down here in the bottom. In both airplanes, it's equals 1 gallon per side. And that's the same as 2 gallons total. And that's there because when you drain the fuel, or when you're draining fuel out of the tank, doesn't want to let me get rid of it. Why won't it let me? When you're draining fuel out of the tank, you want to be able to drain water and sediment, water and crud out of there, and you need that drain at the very, very lowest part of the tank. So you could say the tank drain is at the lowest part, or you could say it's at the bottom of the tank. And the pickup tubes for the fuel is about 1 inch, that's not an exact number, about 1 inch above it, so it's getting clean gasoline. So hopefully if there is any water or sediment in there that you didn't get, it's still pulling in clean fuel. And of course there's another fuel gauge here. Here is the primer pump. We'll just call it the primer. That's what's in the cockpit. It's a manually operated valve, and we're going to call these the primer nozzles. We're going to talk a lot more about them when we get to engines. And while we're here, this square is a carburetor. The thing I like about the word carburetor is none of the vowels get repieced. Carb, et, or. All we need is an I, and and a Y, and we'd have all the vowels in there. And of course, we have a mixture control that goes to the carburetor. We have a throttle control that goes to the carburetor. We're going to talk a lot more about the carburetor and the mixture control when we get to engine theory. So fuel comes out of one of the tanks. Let's say it's set on right. Fuel goes up here, and this is the fuel strainer. It's also known as the gascolator. It's like a very, very fine screen mesh. You could even say it acts like a filter, but usually this isn't a filter where you change an element. This is just a a screen, like a window screen, except the holes are really, really small. That's to get out any last-minute contaminants that maybe you didn't drain. And then there's the strainer drain. And what's significant about the strainer drain is that it is the lowest in the system. That is, in the fuel system, this is lower than everything else. So in theory, you're going to get the water and the sediment to get out of there. We're going to have our electric fuel pump. And we have our engine-driven fuel pump. Tell you what, you don't need to write the word fuel in there. It's an electric pump. There we go. And right here is our pressure sender. And that pressure sender is telling the fuel, the pressure gauge. So here's our fuel pressure gauge. It's sending electrical signal to the gauge so we know what the fuel pressure is, and it's telling you the pressure after, oh, that was interesting. It's telling us our fuel pressure after both pumps. Also, what you need to know about the pumps, oh, that's rather interesting, is that when the engine-driven pump is working, it's going to pull the fuel through the electric pump. Or if the engine-driven pump isn't working, the electric pump will push the fuel through the engine-driven pump. So there's a valve in here that allows fuel to go through it, even if either one of these is broken. So if one of them breaks, the other one will either push or pull fuel through it and get it from the strainer all the way to the carburetor. You'll also notice that the primer gets its fuel after it goes through the fuel strainer. So in theory, the primer, the pumps, and the carburetor are all protected from crud or from sediment by the fuel strainer. Let's see. I want to talk about, I think it's going to be on the next slide. Well, we'll put it on this one here. When do you have these pumps? Here's the engine-driven pump, and there's the electric pump. There's really 3 times electric pump needs to be on. Is takeoff and landing, whenever you're maneuvering low to the ground, and whenever you're switching tanks. Just to make sure when you switch tanks, I think it's going to try to exit. Oh, darn. All right. Well, we'll keep going. Whenever you switch tanks and you go from right to left, you ought to turn on the electric boost pump. So just in case, when you switch tanks, if there's an air bubble in here, it'll go ahead and push the air bubble through, and then right behind it, more fuel. So those are the 3 times that you would need to have the electric boost pump on. And of course, we also probably remember that the engine-driven pump, it's bolted directly to the engine. So if the engine's running, then the engine-driven boost pump is on. I can stop trying to do that. And then the last thing are capacities. So if you've got a PA38, it's 15 plus 1, 15 plus 1 equals 16 gallons per side. That's 32 total. But you notice I put the plus 1 in here because that is unusable. So really you could argue that that equals 31 usable. If it's for a PA28, then in a PA28 it's 24 plus 1, and 24 plus 1 equals 25 per side equals 50 total capacity. But again, this one on either side, that equals 2 gallons unusable, which is therefore going to leave us with 48 usable. So like I said, both airplanes have 1 gallon in each tank you can't use. So 48 versus 50 and 30, correction, I made a mistake there, 30 usable, thank you. 30 usable versus 32 total. And both airplanes have a total of 2 unusable. So we covered unusable fuel. That's a gallon per tank, or a total of 2 gallons per airplane for both airplanes. The engine-driven pump is on whenever the engine is running. You can't turn it off. The 3 times electric fuel pump needs to be on is when you're taking off and landing, when you're maneuvering low to the ground, and when you're switching tanks. You actually want to turn on the fuel pump before you switch tanks if you're in the air. It's a good habit pattern to get on when you're on the ground. And the lowest point in the fuel tank is the drain, the sump drain or the tank drain. The lowest point in the entire fuel system is the drain that's on the fuel strainer on the side of the airplane. That's the lowest point in the entire fuel system. And we just covered fuel tank capacities. We could call it 15 plus 1. 15 plus 1 equals 32 total, less 2 unusable equals 32 usable, or 24 plus 1, 24 plus 1, of course that's for BA28. For 38, so we have 25 plus 25, that's 50 total, minus 2 unusable is 48 usable. Yay, usable. All right. Let's talk a little bit about aviation fuel. Aviation 8087 avgas was red. It's not available anymore. I'm not going to ask you that color. 100 low lead avgas is blue. I am going to ask you about this on the test, and you'll need to know it for your oral practical. 100, 130 avgas was green, but nobody makes it anymore, so I'm not going to ask you about it. And jet fuel, we're not going to pump any fuel into the aircraft that's jet, but it's actually straw colored, a light yellow, very light yellow. It is good data to know about how dense fuel is. Aviation gasoline is 6 pounds per gallon, so a gallon of gas by volume equals 6 pounds of avgas. That's good to know, so you know how much weight is getting put on board the airplane. I'm not going to ask you about jet fuel, because you're not going to be flying jets. But it is good to know what water weighs more per gallon, so it's more dense. And that's why it sinks to the bottom of a fuel strainer cup. So here's your fuel strainer cup, and here's the fuel level. You might see water bubbles down here in the bottom because the water is more dense. And how can you prevent getting things contaminating your fuel? Well, make sure they pump the right fuel in there. Getting jet fuel in your tank is terrible. There's nothing you can do about it except cancel the flight and call a mechanic, and they're going to have to drain all the fuel and flush all the jet fuel out. So there's absolutely none left before you're ever going to get to go flying. Let's put it this way, you're not flying that day. Keep the caps on and keep them tight. If you're not either looking in the tank or putting fuel in the tank, the caps need to be on and tight. That way dirt and dust and insects can't fly in. And if it's raining, then water can't get in. If it's snowing, then snow can't get in. If it's going to get cold, let's say here's a fuel tank. And let's say the fuel level is down here. There's actually water vapor, evaporated water vapor in the air inside the tank. If it gets colder, some of this water vapor is going to condense on the side of the fuel tank, just like drops of water on the side of a can of soda on a cold soda on a humid day. And then these drops might just stick there, and when you go flying and the fuel sloshes around, that's when these water droplets may go down, and if there's enough of them, it might go into your fuel inlet tube. So to prevent that, what you can do is fill the tank up completely with fuel. Fill the tanks up, and now there's no water vapor in there, and so now no water vapor can condense inside the tank. Before you do that, ask your flight instructor what is the normal procedure at the place you're renting airplanes to see if they want you to have the tanks filled up for the night before. The downside of filling off the tanks at night is the next morning, if somebody needs to go and they need there to be half tanks, then they won't be able to take the airplane because the tanks are full. So don't fill up the tanks unless you talk to your instructor first. Okay, let's see. So you can get rid of, if there is fuel contamination, of course you drain each tank. And then, of course, you're going to drain the lowest place in the fuel system, the strainer, which is also called a gasculator. And you're looking for blue dye in your 100 low lead fuel. If it's clear or yellow, then it might be jet fuel or car gasoline, and you wouldn't like that because that's just not safe. That's against the law. And that's it.